urban planning and building energy optimization, are traditionally bottlenecked by slow, manual pipelines. You pull satellite imagery, run GIS workflows, annotate land use, calculate density ratios, and cross-reference everything against ground truth surveys. It's accurate, but it doesn't scale. What if we could skip the manual grunt work and let large vision language models directly interpret aerial imagery to quantify urban structure? That's exactly what this research investigates. We're looking at how state-of-the-art VLMs handle quantitative reasoning over remote sensing imagery, specifically for built environment metrics that directly impact building energy planning, cooling demand, and urban heat mitigation. The results reveal a stark reality. Zero-shot inference barely beats random guessing, but with targeted, parameter-efficient fine-tuning, we can unlock highly reliable, scalable urban analysis. Let's break down how they built the benchmark, why domain-specific models surprisingly underperformed, and what this means for the future of AI-driven smart cities. To understand why this matters, we need to look at what's actually in a satellite image. High-resolution aerial views aren't just pictures of rooftops and trees. They contain structured geospatial information that dictates energy consumption. Building density, impervious surface coverage, and the ratio of green to blue infrastructure directly influence heat retention, local microclimates, and HVAC load. Traditionally, extracting these metrics requires time-consuming computer vision pipelines, manual ground truthing, and heavy domain expertise. Recent advances in remote sensing vision language models have shown promise in captioning and semantic segmentation, but there's a critical gap: quantitative reasoning. Can a model look at a 450 by 450 meter tile of urban sprawl and accurately estimate the building footprint ratio, the impervious space percentage, or the green-to-blue infrastructure index? Most VLMs excel at object detection and high-level description, but they struggle with proportional estimation, spatial composition, and numerical decoding. This benchmark was designed specifically to test those grounded quantitative capabilities. The researchers constructed a large-scale benchmark by merging two primary data sources. High-resolution remote sensing imagery from Mapbox and land use polygons from OpenStreetMap. They focused on the 335 largest U.S. metropolitan areas, extracting 672 by 672 pixel tiles at zoom level 17. For each city, they generated a 4x4 grid centered on the urban core, capturing up to 16 images per location to cover diverse urban contexts. They paired these images with derived built environment metrics, including building footprint ratio, green area percentage, urban blue area percentage, impervious space ratio, and several composite indices like the blue-to-built ratio and green-blue index. These metrics were formulated as multiple-choice visual question-answering tasks. Instead of open-ended generation, which introduces too much variance, they used carefully constrained candidate answers within realistic ranges. The final dataset contains over 14,000 images and more than 100,000 question-answer pairs, split into training and testing sets. Now, let's get into the technical execution. The team evaluated a diverse set of state-of-the-art vision language models, spanning general-purpose architectures like LoRA-VA16, Intern VL3, QNVL3, and MGM, alongside remote sensing-specific models like GeoChat, VHM, and Falcon. To adapt these models, they used parameter-efficient fine-tuning via LoRA. Specifically, they applied low-rank adaptation with a rank of 32 and a scaling factor of 16, targeting the query and value projection layers in the attention modules. Training ran on 4 NVIDIA B200 GPUs using the Atom W optimizer with a learning rate of 5 × 10 to the -5th, weight decay of 0.01, and gradient accumulation over 8 steps. They trained for 2 epochs with a 5% warm-up, followed by cosine or linear learning rate decay, all in mixed precision FP16 using PyTorch and Hugging Face transformers. This setup was chosen to prove that you don't need massive compute budgets to adapt foundation models for geospatial tasks. The zero-shot results were stark. Without any fine-tuning, model accuracy hovered around 25 to 45%, which is only marginally better than random selection for a 4-option multiple-choice setup. Adding explicit semantic cues in the prompt, like specifying green or percentage, provided a slight bump, but it wasn't enough to overcome the fundamental gap in quantitative spatial reasoning. However, after domain-specific fine-tuning, accuracy jumped by roughly 90% across the board. General-purpose models like Intern VL3 and QNVL3 consistently led the pack, with green area percentage reaching over 72% accuracy. Why? Because vegetation has clear visual semantics and aligns well with linguistic representations. Metrics involving explicit numerical targets like percentage also performed better because they give the language model a concrete decoding objective. But here's where it gets interesting. Despite being explicitly trained for remote sensing, the domain-specific models like GeoChat and Falcon did not consistently outperform general-purpose vision language models. This points to a systemic issue in how domain knowledge is currently injected into foundation models. Existing tuning strategies for geospatial imagery seem to prioritize semantic captioning over structured quantitative reasoning. The models haven't been adequately trained to translate aerial visual patterns into precise spatial proportions. This suggests that future remote sensing VLMs need better mechanisms for incorporating structured domain knowledge, particularly for numerical estimation and relational reasoning over built environments. Simply adding more satellite images to the per-training mix isn't enough if the alignment between visual features and quantitative labels remains weak. The study also uncovered a critical dependency on data quality. Performance varied noticeably across cities, and this wasn't strictly correlated with city size. Instead, the bottleneck was the completeness and accuracy of OpenStreetMap land use annotations. In regions where OSM data was sparse or misaligned with actual imagery, the derived metrics introduced noise, weakening the image metric alignment and dragging down model performance. This is a crucial reminder for anyone deploying AI in urban analytics. Model architecture is only as strong as the ground truth data it's trained on. Improving the reliability of open geospatial datasets is just as important as scaling model parameters. If you want quantitative reasoning to work at scale, you need clean, consistent, and spatially accurate labels. So what does this actually mean for smart cities and energy planning? It means we're moving past the era where AI can just describe a neighborhood. With targeted fine-tuning, vision language models can now quantify urban structure at scale, enabling rapid assessment of building energy potential, heat island mitigation strategies, and infrastructure optimization. The path forward isn't just about bigger models. It's about better alignment between visual encoders, quantitative reasoning heads, and high-quality geospatial ground truth. If we can close that gap, we unlock a new paradigm for data-driven urban planning, where satellite imagery and large language models work in tandem to make cities more efficient, resilient, and sustainable. If you're working at the intersection of geospatial AI, urban analytics, or multimodal foundation models, this is a critical benchmark to keep on your radar. Let me know in the comments how you think domain-specific tuning should evolve to handle quantitative spatial reasoning. And don't forget to subscribe for deep dives into the latest AI research that's actually moving the field forward.